Hello everyone. In this video, I am explaining 8086 microprocessor and 8259 programmable interrupt controller interfacing, in which 8086 is operating in minimum mode and 8259 is operating in single mode. That means only one single 8259 is connected to 8086 microprocessor. So this is block diagram of, you can see here, this is block diagram of 8259 programmable interrupt controller. So whenever we connect this interfacing IC to any of the microprocessor, always remember that we connect processor on the left hand side and we connect devices on the right hand side. So this is 8259 and here you can see there are 8 interrupt request pins are available on 8259, that is from IR0 to IR7. You can connect 8 interrupting devices from device 1 to device 8 to interrupt request pins of 8259 programmable interrupt controller. Now first of all, let's see how to connect 8086 in minimum mode. Now this is minimum slash maximum bar pin of 8086. This is maximum is active low and minimum is active high, and here we have to connect here logic 1 because we want to use 8086 in minimum mode. 8086 in minimum mode means in a system there is only one 8086 operating. On left hand side of 8086 we connect clock generator IC, that is 8284. To 8284 there are two pins, that is X1 and X2, and to these pins crystal oscillator is connected. This crystal oscillator generates clock frequency for 8086. Let's say suppose frequency of this clock signal is 15 megahertz, then 8284 will divide this frequency by 3 and remaining clock frequency is given to 8086 microprocessor. That means, say, suppose here we want 8 megahertz of frequency to be applied to 8086. In that case, this frequency should be 24 megahertz. The ready pin of 8284 is connected to the radio of 8086 and reset pin of 8284 is connected to the reset pin of 8086. Now you can see here the ground is connected to the ground and VCC is connected to 5 volt. Now what are the connections on the right hand side? Now in 8086 you know that this is address bus. AD0 to AD15 is address data multiplexed bus and A16 to A90 is pure address bus. Now what is meaning of address data multiplexed bus? Address data multiplexed bus means in the beginning on that bus it will carry address and in the next half the same bus carries data. Now what is bus? Bus is bundle of wires. Wires carries data. Wires carries information. Information means logic 1 and logic 0. So on this bus, in these 16 wires, initially the address will flow and in the next half the same bus carries data. So when the same bus carries data, the system may lose a address flowing in the system, and hence to store that address we need octal latches. 8282 is octal latch. Octal latch means one IC holds 8 bit of address. So this IC is used to store this address flowing on the address bus. Since one IC holds only 8 bit of address, we need 3 octal latches, which is connected to AD0 to AD15 and A16 to A19 pins of 8086. Address latch enable pin of 8086 is connected to the strobe input of this octal latch, and this is pure address bus A0 to A19, that is 20 pin address bus. When this pulse, short pulse, flows on this pin, and when strobe input of this latch receives this pulse, it will activate this latch, and whatever address is flowing on this address bus, it will hold that address. It will lock that address inside. This is 8259, that is programmable interrupt controller. We know that there are 8 interrupt request pins, that is IR0 to IR7. Say device 1 is connected to interrupt request 0 pin. This is 8286 bus transceiver IC which is connected to the data bus of 8086, and this side is connected to D0 to D7 data bus of 8259. Now these are only buffers. It is used to transmit and receive the data or information. This 8286 decides the direction of data flow. How it decides the direction of data flow? The data transmit slash receive bar pin of 8086 is connected to the transmit pin of 8286. Transmit is active high and receive is active low. Whenever 8086 wants to write something into the 8259, it is said that it is a transmit operation, and that time it should transfer logic 1 on this pin. And whenever 8086 want to receive some data or read some data from 8259, it is said that it is receive operation, and that time logic 0 should flow on this pin. Data enable bar pin, which is active low, which is connected to the OE bar pin of 8286. Now here we are using two ICs of 8286 because size of data bus is D0 to D15, that is 16-bit data bus. And that's why one can be connected to 8 pins, and hence here we need two 8286 ICs. Now when logic 0 flows on this pin, then it will activate this 8286. And when 8086 wants to receive a data or read the data from 8259, it will transfer logic 1 on this pin. Suppose 8086 wants to write something, that time it will transfer logic 1 on this pin. Now here you can see there are three more pins of 8086, that is read bar, write bar and memory slash IO bar. Whenever 8086 wants to write something on in 8259, the write bar pin should be at logic 0, and when 8086 want to read something, the read bar will be at logic 0. If we connect memory to 8086, memory is active high, this pin, on this pin the logic 1 will be transmitted, and when 8086 is connected to input output device, input output is active low, so 8086 will transmit logic 0 on this pin. So these pins perform the function of memory read, memory write, input output read and input output write. 8259 is input output device. This is 3:8 decoder. All these three pins of 8086 are connected to 3:8 decoder, and based on the status of what is there on this, that is whether this is 0 or this is 0 or this is 0, it generates different control signals for 8086 microprocessor. This decoder generates different control signals for 8086 microprocessor. Remember that at a time either write bar will be 0 or read bar will be 0. Both cannot be 0 at a time. Now since 8259 is not a memory but input output device, the memory write and memory read is not connected. The input output read of this decoder is connected to read bar of 8259, and IO write is connected to 82 write bar of 8259. 8259 has interrupt pin, that is INT pin, which is active high, which is connected to the INTR pin of 8086, or we can also connect to the non-maskable interrupt, that is NMI input or NMI pin of 8086. The interrupt acknowledgement pin of 8086 is connected to the interrupt acknowledgement pin. This is interrupt acknowledgement pin of 8259. Whenever, now suppose let's take an example that 8086 is executing its main program. It is executing some main program which is stored in the memory. Now device 1 also wants to execute some program which is stored in the same memory which is connected to 8086 but at different location. Device 1 wants to execute this program, but this is a device, it is not processor, and hence it cannot execute this program. So what device 1 does, it wants the help of 8086 because 8086 has a brain, it is intelligent and device and has a capacity of execution of program. So device 1 will send the request for execution of this program to this 8259 first by sending logic 0 on by sending logic 1 on IR0 pin to 8259. When 8259 receives logic 1 on this, it understands that device 1 wants the execution of this program. What this program is known as? This program is known as interrupt service routine, or it is also said that it is a subroutine, interrupt subroutine. And whatever program 8086 is executing, it is said that it is a main program. Remember that both programs are in the same memory but at different memory addresses. When 8259 receives logic 1 on this pin, it will send interrupt request on INT pin. Concentrate here, it will send interrupt request on INT pin to 8086 on INTR pin. 8086, if it is executing this program, when it receives this interrupt request, let's say 8086 is executing some instruction. So first it will complete the execution of this current instruction of the main program, and then will send acknowledgement by sending logic 0 on INTA bar pin to 8259, indicating that okay, I am ready to execute your program. So it will transmit logic 0 on this pin to INTA bar pin. Now this is CS bar pin of 8259, which is chip select bar, which should be 0 if 8086 wants to use this particular 8259. And here you have to connect a decoder logic. Decoder logic may be consist of 3:8 decoders or logic gates that will be different for different users. A1 pin of this address A0 to A19 is connected to A0 pin of 8259. Now we have seen when device 1 sends a request, 8259 sends interrupt request to 8086. But now let's see what happens inside the 8259 when it receives logic 1, and how it transfers this interrupt request on INT pin to INTR pin of 8086 microprocessor. So let's see step by step. Now again we'll see device 1 is connected to IR0, device 2 is connected to IR1, device 7 to IR6, and device 8 to IR7. Now when device 1 sends interrupt request on IR0, the IR0 corresponding bit, this is interrupt request register of 8259, the IR0, it is a 8-bit register. Interrupt request register is 8-bit register, and for every interrupt request pin, there is a corresponding bit position. As soon as it receives interrupt request on IR0, it will set the IR0 pin. When it receives request on IR1, it will set IR1 pin. And when it receives request on IR7 by device 8, it will set this bit. All other bits will be at logic 0, as no devices are connected, or even if devices are connected, there is no interrupt request on that pins. Now what happens next? After interrupt request register, we know that now IR0 is 1, IR1 is 1, and IR7 is 1. So interrupt request register will provide this information to priority resolver. Now what priority resolver does? Priority resolver will check whether these interrupts are masked or allowed, masked or unmasked. Masked means these interrupts should be blocked. It should not be forwarded further to processor. And allowed means okay, enabled means okay, these interrupts you can forward further. So when priority resolver receives this information from interrupt request register, now it will check interrupt mask register. Now interrupt mask register, these bits are 0. You can see here these bits are 0, IR2, IR3, IR4, IR6 and IR7. That means these are unblocked. That means these interrupts are enabled. But IR0 is 1. It is 1 means the interrupt coming on IR0 indicate 1 on this bit indicates that the interrupt received on this pin should be blocked and it should be masked, and hence priority resolver will not forward this interrupt on IR0. Now IR1 is also 1, so it will not transfer, that is IR1. This interrupt it will not transfer to the processor. Now IR5 is also 1, but there is no interrupt request on that pin. So there is no interrupt request, so it is 0. So it has to do nothing with that. Now there is an interrupt request on IR7 pin and it is 0. That means it is allowed. So priority resolver will select this IR7. Now it will check the status of interrupt request register. Now interrupt service register. In interrupt service register, all bits are 0. It indicates that there are no higher priority interrupts going on, and it indicates that there is no pending interrupt, and 8086 or processor is free for receiving any of the interrupt available with priority resolver. So priority resolver will transfer this IR7 interrupt to control logic. So we have seen interrupt request register, it was blocked, that is IR0, and IR1 was avoided, and it has forwarded IR7, that is priority resolver forwarded this to control logic, and that's why it is at logic 1. Now control logic will transfer interrupt request. This you can see here, concentrate, this is one which is connected to INTR. I will show you one more time. It will transfer interrupt request to 886 on INTR pin. When 886 receives logic 1 on this pin, it will first, if it is executing the program, first it will complete the execution of current instruction. Whatever program it is executing, if it is in between of some instruction, first it will complete the execution of that instruction, and then it will transfer acknowledgement by sending pulse on INTA bar pin to 8259. When 8259 receives this pulse on INTA bar pin, what it does first, it will set interrupt request register or in service register. It will set this IR7 pin, indicating that IR7, the interrupt on IR7 is in process. This bit 1 indicates that the interrupt received on device from device 8 on IR7 is in process. After that, once it is set, once this in-service register bit is set, now it will reset this IR7 of interrupt request register like this. It will reset this and it will make it 0. 0 means now again it is ready to receive next interrupt on the same pin. After that, what control logic does? Control logic will send a code of call instruction to 886 microprocessor through data bus. After 886 receives this, it will send again one more INTA bar pulse. One more, after 886 receives this, again it will send second INTA bar pulse to 8259. When 8259 receives this INTA bar pin, what it does, it generates one code. It sends one code to 886 microprocessor. What this microprocessor does, microprocessor will multiply this code by 4 and it will generate and it will store these contents into code segment register and instruction pointer that will give you this 886 the address of interrupt subroutine. That means wherever this device 8 program is stored, the address of that will be generated by multiplying this code by 4 and it will get stored in code segment register and instruction pointer. At the same time, when it receives this negative pulse, it will reset this IR7 pin. Now let's assume that like 886 was executing the main program. It is memory. In memory here main program is stored and this is subroutine. Subroutine means program for this interrupting device. It is interrupt service routine or interrupt subroutine. Okay, so this was a program. It is at different address and this is at different address. So what happens? 886 first it was executing its main program, and whenever it received the interrupt on INT pane, what 886 will do, it will send the acknowledgement, then it will receive this code, it will multiply this code after the enter process, it will multiply this code and it will give the address for this subroutine wherever it is stored in the memory. So this is how 8086 communicates with this interrupting device. You can see device 8 wanted to execute the interrupt service routine and it has sent the request on this pin. This interrupt request register transferred that information to priority resolver. Priority resolver checked for interrupt mask register, then it checked interrupt service routine, then it sent interrupt to control logic, then it sent it to 8086, then 8086 sent negative pulse to 8259, then it has set this bit, then it has sent this call address, then 8259 sent this code, vector code, then it has multiplied it with by 4, stored this information in CSR register and instruction pointer, and generated the address of interrupt service routine, and then it has resetted this bit. So this is how 8086 communicates with interrupting device by using 8259 programmable interrupt controller. So I hope you understood the concept and how it communicates. I tried to make it as easy as possible. It was explanation of when 8086 operates in minimum mode and 8259 operates in single mode. Now next video will understand when 8086 operates in minimum mode but 8259 is connected in cascade mode. Then half of the explanation and communication will remain same. Only difference will be 8259 communicating with 8259. So thank you very much. Thanks for watching. If you have any doubts, you can always ask in the comment section. Thanks.